Alright, so a couple of things we can pull from an equation about its graph. When we talk about horizontal tangent lines, we know that the derivative is equal to 0, the slope is 0. More specifically, what that means is your numerator is equal to 0, but obviously your denominator cannot because that's a problem. So it's when your numerator is set equal to 0. Vertical tangent lines occur when the denominator is equal to 0. Numerator cannot be equal to 0, so it's when the denominator is equal to 0. And then tangent lines do not exist when both numerator and denominator are equal to 0. And these points must be thrown out. So let's look at this function. It says find the slope of the graph. It's y cubed plus y squared minus 5y minus x squared. So it equals -4. At the point 1, -3, by first finding dy by dx, and then evaluating at the 1, -3. Now, if we scroll down to the bottom here, this is actually the crazy graph of this function. We're looking at 1, -3. So if we go to 1, we're down here. And we want to see what's happening at this tangent line that's right here on the graph. We're going to figure this out. But if we actually looked at the value when x is 2, notice there's actually a tangent line here, there's one here, and there's one here. So that's why you actually get the y value for this slope that we're looking for, because there could be more than one tangent line at that 1x value. Okay, so let's go ahead and differentiate. We have to do it implicitly because we cannot solve this for y easily. Okay, so we're going to do both sides. Take the derivative in terms of x of y cubed plus y squared minus 5y minus x squared. And then we take the derivative of the right hand side also. So here we have to do each part separately. We're going to do the chain rule here. So we have 3y squared times dy by dx. So remember, chain rule is f prime of g of x times g prime of x. And that's what we just did here. We're going to add 2y times dy by dx minus 5 times dy by dx minus x squared. So we're differentiating with respect to x. And remember, on the right side, we're differentiating a constant. Differentiate a constant with respect to any variable is always going to be 0. We want to rearrange by finding dy by dx first. So let's rearrange or gather our like terms here. Notice that we have a dy by dx here, here, and here. So I'm going to move this to the other side. And I'm going to do some algebra here because the calculus is done. Algebra at this point is now I'm going to factor out a dy by dx. So dy by dx, and we have 3y squared plus 2y minus 5 equals 2x. And then dy by dx, which is what we're going to use to find the slope, becomes 2x over 3y squared plus 2y minus 5. And from there, we want to evaluate when x is 1 and y is -3. So dy by dx equals 2 divided by, and put -3 in, squared times 3 is 27, minus 6 minus 5, or 27 minus 11. So that's going to be 2 over 16, or dy by dx is 1/8. So this is a rise of 1 and a massive run of 8. So we're going to look back here, just having a quick scan at 1, -3. We could probably agree that 1 over 8 would make sense according to this picture of the graph that we have. Alright, example 3. Find the slope of the graph. Same one at the same point, but this what we're asking you to do is differentiate first, then plugging in 1, -3 before solving for dy by dx. So here, let me pull this down here. I'm going to move this, just use it really quick. So we have done the first part. We're just going to hold on, drop my d there. Alright, substitute in, so we have 3 times y squared, so that's going to be 27 dy by dx, plus negative 6 dy by dx, minus 5 dy by dx, equals, so 2x, so 2. And then here, dy by dx, well actually pulling this together is going to be 16 dy by dx equals 2, therefore dy by dx is 1/8. Notice obviously we get the same slope because it's the same problem. It's just if it's not asking you to solve for dy by dx, so this one specifically said, first evaluate by finding this, solve for dy by dx, so basically give me the equation for the slope at any point for that graph. Here they just want the slope, so that's one way we can do it. And the very last piece is identify the x values for both horizontal and vertical lines. So remember, horizontal lines is when the derivative equals 0, so your slope is 0. We'll go back to vertical tangent lines in a moment. So that means the numerator is equal to 0. So we have 2x. Actually, hold on. dy by dx equals 2x over, so it becomes 0 equals 2x, or x equals 0. So here you can see that this should be a horizontal tangent line like there, proven by our equation. Vertical tangent lines, if we look back here, is when the numerator is equal to 0, not the denominator, the denominator, not the numerator, the denominator is equal to 0. Denominator in this case is 3y squared plus 2y minus 5 equals 0. And maybe we can factor this and get our values. Maybe we can use the quadratic formula, even though it's not in terms of x, it's still a quadratic form, and then get our values for x by putting them back in. It's just something to be thinking about.